Hello students, welcome to EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module which consists of a discussion on factor groups, normal subgroups and direct product of groups from a paper, Mathematical Physics. So students, let us see what are we going to learn in this module. We are going to learn more mathematical preliminaries relevant to the study of group theory, learn about the normal subgroup and the factor groups, and the students would then be introduced to the direct product of two groups. The concept of conjugate class is an important concept in the sense that a group can be splitted to sets of such that all the elements of set 1 conjugate to other. However, two elements belonging to different sets are not conjugate to each other. Given a subgroup H of a group G, we can construct a set of elements GH, G inverse, with H, an element belonging to the subgroup H, and G belonging to the group G whose subgroup is H. For elements G, which are also in H, GH, G inverse is obviously the set of elements in H. However, if the set of elements GH, G inverse are the same as the elements of a subgroup H for all elements G belonging to the group G, then the subgroup is called the self-conjugate group. It's also called an invariant subgroup or a normal subgroup. An important classification of groups is the following. A group which has no invariant subgroup is called a simple group. Simple groups are of great importance when we discuss continuous groups. Theorem. Self-conjugate subgroups have the following important property. The left and right cosets of a simple conjugate subgroup are equal. The proof is as follows. We have for a self-conjugate subgroup H of G, the definition that GH G inverse is H for all G belonging to G. Hence, for an element H1 which belongs to the subgroup H, any element G1 which belongs to the group G, we can find an element S2 belonging to the subgroup capital H such that G1 H1 G1 inverse is equal to S2 or G1 H1 is equal to S2 G1. The set of elements on the left hand side is just the left coset G1H, and the elements on the right hand side constitute right coset. It should be borne in mind that the last equality is in the sense that the two sets are equal. It does not imply that G1 commutes with all elements of the subgroup H. That is, G1H is equal to H G1 for all H belonging to H is not implied. So the result is that the left coset is equal to the right coset. We will illustrate this with the help of an example. Again, we will take the symmetry group S3 as our model to explain what we discussed just before. The group S3 has a subgroup H which consists of three elements E, D and F. This subgroup of H is an example of a normal subgroup. To see this, first let us convince ourselves that the subgroup consisting of the element EDF is indeed a subgroup. That is, it satisfies all axioms of the group. The multiplication table shows that EE is equal to E, where E multiplied by D is D, D multiplied by E is D, and so on. That DF is equal to E, FD is equal to E, DD is equal to F, and F is equal to FD. This establishes that these three elements satisfy the property of closure, which establishes that H is a subgroup. The left and right cosets of H can be constructed by using the multiplication table. For example, the left cosets are EH, AH, BH, CH, DH and FH. And from the multiplication table we can see that all these cosets consist of elements. For example, the coset EH consists of EDF, the left coset AH consists of element ABC, and so on and so forth. Similarly, we can construct the right cosets as can be seen in the slide. HE is equal to EDF, HA is equal to ACB, HB is equal to BAC, HC is equal to CBA, HD is equal to DFE, HF is equal to FED. Now we can easily see that the right coset GH is equal to left coset HG, hence H is a normal subgroup. We will now show that for an abelian group, every subgroup is a normal subgroup. The proof is simple. Let G be an abelian group and H be any possible subgroup of G. Then for every G belonging to the group G and for every element H belonging to the subgroup H, we have GH G inverse is equal to HG G inverse because G and H commute. Group abelian, which is equal to H, which belongs to the subgroup H. Thus, GH G inverse is equal to H, hence H is a normal subgroup. If a subgroup is a group which has index 2, then it is necessarily a normal subgroup. Can be seen as follows in the slide. Let G be the group and H is a subgroup. Then the set of elements GH with G belonging to the group G but not to H, and with H belonging to the subgroup H, then GH is a left coset. The left coset must be the set of elements in G that do not belong to H, since the index of H is 2. Therefore, the group G is equal to H plus the group formed by GH. Similarly, for the right coset, the group G can be written as the subgroup H plus the group formed by HG, and GH is equal to HG. Okay, let us now define the center of the group. What is meant by the center of the group? The center of group, which is written as Z of G, is the set of all those elements which commute with all the elements of G. That is, the group G has number of elements which is equal to the order of this group G. A subset of this group G which commutes with all the elements of the group G forms the center of the group G, which means that Z of G is a set of elements H which belong to the group G such that every element of H commutes with the element of G. That is, if H is the element of this subgroup H and small g is the element of the group G, then HG is equal to GH for all elements G belonging to the group G. Now, for abelian groups, every subgroup is normal. Why? Because every element of an abelian group is on conjugacy class. How do we say that? Consider that the two elements G1 and G2 belong to the group G. Then, since the group is abelian, the product of these two elements G1 and G2 is the same as the product G2, G1. Multiplying the left hand side and the right hand side by the inverse of the element G1, we have G1, G2, G1 inverse is equal to G2 into G1, G1 inverse, which is equal to G2. Therefore, G2 is equal to G1, G2, G1 inverse. What does it mean? From the definition of the conjugacy class, it means that G2 is its own conjugacy class. Likewise, from the property of the identity element, GE is equal to EG, then multiplying the left and right hand side by the inverse of G, I have GEG inverse is equal to EGG inverse, but GG inverse is E because G is an element of the group, and E into E is E, which means that E is equal to GEG inverse, and therefore E is on conjugacy class. The center is always a normal subgroup. Now, if a group has no non-trivial subgroup, what are the trivial subgroups? Trivial subgroups are the identity and the full group G itself. So, if there is no group which has any other subgroup apart from the identity and the whole group itself, then the group is called a simple group. We will now discuss multiplication of cosets. If H is any subgroup of G, left cosets as defined before are the sets of elements GH, where G is any element belonging to the group G but not to the subgroup H. If GI and GJ are two such elements of the group G from the set E, G2, Gn, etc., then the product G1, GIH, GJH are the set of elements obtained by multiplying the elements of GIH with those of the set GJH. In general, the set GIH, GJH need not be a coset of the group G. But if H is a normal subgroup, then the set GIH, GJH is a left coset of G. Can be seen as follows. Since for a normal subgroup H, the set of elements GH is equal to HG for any G belonging to the group G, GIH, the proof of the above statement is simple. Since for a normal subgroup H, the set of elements GH is equal to set of elements HG for any G belonging to the group G, then the set of elements obtained by multiplying GIH with GJH is equal to GIGJ HH. But HH is equal to H and GIGK is equal to GK. So therefore this is equal to GK is a set consisting of the elements GKH, where GK is equal to GIGJ belongs to G, and obviously H belongs to H. Since neither G1, GI nor GJ is an identity element, GK is not equal to GI or GJ. Thus the product GIH, GJH is either H if GI is equal to GJ inverse, or a new coset different from GIH or GJH. Define the factor group, and first the definition of the factor group. When a group G has a normal subgroup H, there exists an important group called the factor group. The last result for a normal subgroup leads to a new group structure. Let H be a normal subgroup of G, and let a set of defined as G by H denotes the set of all left or right cosets of H in G. We now prove that the set G by H is a group with respect to the group multiplication rule. Remember that The set denoted by G by H has the elements which are now cosets. The following multiplication rule holds. AH multiplied by BH is equal to ABH for all elements A and B belonging to the group G. We have already proven that if A prime is equal to AH for some element H belonging to the subgroup H, then the coset A prime H is equal to AH. Similarly, if B prime is equal to B times H1 for some H1 which also belongs to the subgroup H, then B prime H is equal to BH. For the definition of group multiplication of cosets to be well defined, we must now prove that A prime H into B prime H is equal to A prime B prime H is equal to ABH is equal to AH into BH. We will now define the order of a factor group. For a finite group G with a normal subgroup H, the number of distinct cosets is K into G by H, written as capital G by capital H, where G is the number of elements of G denoted by capital G modulus and H is the number of elements of H denoted by H mod. The number of elements of the factor group denoted by mod capital G by capital H is equal to number of cosets, and hence modulus capital G by capital H is equal to capital G by capital H, where capital G is defined earlier as the number of elements of G and capital H is the number of elements of H. We will illustrate what we have discussed above with the help of an example. Consider the symmetric group S3, whose elements are E, A, B, C, D, and F, and whose multiplication table has been given before in the previous modules. The symmetric group S3 has the subgroup capital H with elements E, D, and F, and is a normal subgroup. Its cosets are E, H equal to the elements E, D, F, which is written as a coset capital E, and another coset AH, whose elements are A, B, and C, which is designated as A. The factor group S3 by H thus has two elements, capital E and capital A. The multiplication of this factor group can be worked out from the group multiplication table of the symmetry group S3 and is given by the following table in the slide. It says that the E multiplication of E and E gives E, E with A gives A with E obviously gives A, and A gives E. We will now discuss a very important concept of the direct product of two groups. It's an important concept and used extensively in group theory and its application to physics. Let's consider two groups, GA and GB. The group GA consists of elements A1, A2, A3, AN, where A1 is equal to EA, and the group GB consists of elements B1, B2, Bn, where B1 is equal to the identity element EB. The groups are of order Nm respectively. That is, the group GA has n elements, whereas the group GB has m elements. The direct product of GA written as GA cross GB is defined as GA cross GB is equal to AI dot Bj, where I goes from 1 to n and j goes from 1 to m, with group multiplication defined as AI Bj into AI prime Bj prime. AI Bj are the elements of the direct product group, and AI prime Bj prime some other element of the direct product group. The multiplication is defined as AI Bj into AI prime Bj prime is equal to AI prime, comma, BJ prime. The direct product group GA cross GB clearly forms a group because EA-BG cross AI-EB is equal to AI-BJ, which is equal to AI-EB into EA-BJ, which implies that the group elements of GA commute with the group elements of GB and that GA and GB are subgroups of GA cross GB. Thus, in the direct product of two groups GA and GB, the elements of the group GA commute with the elements of group GB, and the groups GA and GB themselves are the subgroups of the direct product group GA-GB. This can be generalized to define the direct product of two subgroups. Let S and T be two subgroups of G such that S cross T commute with each other. That is, SI-TJ is equal to TJ-SI for all SI belonging to the subgroup S and for all TJ belonging to the subgroup T. We can now define the direct product of these two subgroups S with T as S cross T equal to the elements SI-TJ, where the element Si belongs to the subgroup S and the element Tj belongs to the subgroup T. We will now illustrate how the direct product of two groups operate by taking a simple example. Consider two groups, a group C2 with two elements, the identity E and element C2, where E is equal to 1 and C2 is minus 1. And another group C3 of order 3, whose elements are E, C3 and C3 square, where E is equal to 1. C3 is e to the power 2 pi I by 3 and C3 square e to the power 4 pi I by 3. The direct product of these two groups C2 and C3 consists of the following elements. It consists of E, C3, C3 square, C2, C2 C3 and C2 C3 square. One can work out, see that the elements are E is I, 1. So elements are 1, C3 is e to the power 2 pi I by 3, C3 square is e to the power 4 pi I by 3, C2 is minus 1, C2 C3 is minus e to the power 2 pi I by 3, C2 C3 square is e to the power minus e to the power 4 pi I by 3, which can be rewritten as 1 e to the power 2 pi I by 3, e to the power 4 I by 3, e to the power pi, e to the power 5 pi I by 3, e to the power pi I by 3. So students, we are now in a position to summarize what we have learned in this module. Number 1. If a group has no subgroup, which means that apart from the identity and the whole group itself, there is no other subgroup, then that group is called a simple group. Number 2. We have already shown that for an abelian subgroup, for an abelian group, every subgroup is a normal subgroup because every element is its own conjugacy class. Number 3. If we have two groups, GA and GB, then the group elements of these groups commute among themselves. What does it mean? That if we take an element of the group GA and another element of the group GB, then for any such element belonging to the group A and B respectively, the elements commute among themselves. And in which case, the groups GA and GB are subgroups of the direct product group GA into GB. Thank you.